This is part 3 of our trig equations discussion. This is called substitution of functions. The first thing you notice when you look at one of these equations is for the first time, in example 1 here, we have two different functions. We have a cosine square and a sine square. And everything before now, we've only had one. So for this set of functions, we're going to revisit some concepts from the chapter before where we dealt with trig identities. So I'm going to remind you throughout this discussion of some identities that we had. In fact, for this first problem, I want to remind you of the fundamental identity of trig that says sine square x plus cosine square x is equal to 1. And I'm just going to put that up there in the corner and draw a box around it because we need to remember that. We're fixing to have to use that as we look at this problem. Now, we're not going to be able to work a problem that has a cosine square and a sine square in it. It's just like trying to work a problem that has two variables in it. So what we're going to do is we're going to replace one of these, and I'm just going to choose to replace this first one. Cosine square, if you go back to this fundamental identity and solve it for cosine square, it would equal 1 minus the sine square. And so what I'm going to do is I'm going to replace that cosine square with 1 minus the sine square x. And then I'm going to continue to write the problem. And this is what I have. So again, we replace. This is called substitution of functions. So we're going to substitute in place of cosine square 1 minus the sine square. Now, if you look at this problem, then we're going to have 1 minus 2 sine square x equals 1. Keep going. Negative 2 sine square x is equal to, bring the 1 over and you're going to have a 0. So sine square x is going to equal 0. And sine of x is going to equal plus or minus 0, which is just 0. Now think to yourself, sine x is equal to 0, where y is equal to 0. Let's think for a minute. Where is y equal to 0? Here at 1, 0, and here at negative 1, 0. So our two answers for x should be 0 and pi. Remember, we do not count 2 pi. That is not included in our set. Now, if you think about this, if you want to check, this would be 1 squared minus 0 squared equals 1, and this would be negative 1 squared minus 0 equals 1, so the problem does check. This is substitution of functions where you have to do something, you have to replace so that you can write the equation in one function. All right, moving on to example 2. Notice this is a cosecant squared and this is a cotangent. Again, revisiting the last chapter, remember we had this function, cotangent square x plus 1 equals cosecant squared x. We're going to use that function to substitute into this problem. Now, only one of these is squared. This one is squared, this one is not. So we can replace this with cotangent square x plus 1 equals 2 cotangent x. Now, the good news is we have now made the substitution. We have everything in terms of cotangent. So when we look at it, we're going to take everything over to the right-hand side, cotangent squared x. I'm going to bring this next, minus 2 cotangent x plus 1 equals 0. And we're going to try to factor that. Cotangent x, factors of 1 are 1 and 1. And this is minus and minus. And so this is a double factor we've talked about. They're the same, so we'll just solve for 1. Cotangent x minus 1 is equal to 0. So cotangent x is equal to 1. Now, as we talked about in class today, most people don't care to work with cotangent. So therefore, it's the same thing as saying the tangent of x is equal to the inverse of 1, which is also 1. That message is pi over 4 angles. and tangent is positive in quadrants 1 and 3. So we have two answers for this problem. We have the pi over 4 in 1, and we have the 5 pi over 4 in 3. And either way, we should be able to check that. The cosecant of both is the square root of 2, so you can see that that works. This is example 2. Finally, my last example for this is example 3, and as you can see here, we have tangent minus cotangent equals 0. Now this problem is different from the other two in that it contains no squares. So the Pythagorean identities are out. What we've got is two single functions. You know, when we're looking at something like this, we just kind of have to use trial and error. If we put them on different sides, we get tangent equals cotangent. If we square them, we get tangent square equals cotangent squared, which is unfortunate because they don't have an identity that relates to them. So maybe we could do this. This is just an option. What if we put sine over cosine minus cosine over sine equals 0? It's just an idea. Now, the common denominator here would be cosine theta sine theta. This one needs a sine, so it becomes sine square minus cosine square equals 0. Now, since this is proportional, we can multiply both sides by cosine sine, and we will get sine square theta minus cosine square theta equals 0. That's by cross multiplying. You see this denominator would go out. Now, this one, then we can refer back to our fundamental identity, sine square plus cosine square equals 1. So we could say replace the sine square with 1 minus the cosine square minus the cosine square, which is 1 minus 2 cosine square theta. And let's just finish now. Negative 2 cosine square theta equals negative 1. So cosine square theta is equal to 1/2. I'm running out of room, so I'm going to go up here. So cosine theta equals plus or minus 1 over the square root of 2. Rationalize that. Cosine theta equals plus or minus square root of 2 over 2. You recognize that as pi over 4's all quadrants. And so the answers would be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, there are times when you have to check your answers. We know the tangents and cotangents of these are 1. So what we have to say is the only time that this could be true is if this equaled 1 and this equaled 1. And so we know for this one, that's true. For this one, they're both negative, so let's check that. That would be negative 1 minus negative 1, which would also be true, so that's good. For here, they're both positive, so that's good. And for here, they're both negative, so all 4 answers are okay. That is true. Okay, this concludes my examples of substitution of functions. Thanks for listening, and I'll see you in class tomorrow.